going to talk about data. So to kind of like situate ourselves a little bit I have 60 slides. You can't go through 60 slides without knowing why you're here, because otherwise you'll just like lose attention and collect frogs. So Zurich's thesis for data systems is that essentially in like one sentence, programmable cryptography, so zero-knowledge proof, FHE obfuscation, enables what we call the universal data adapter, which is in some way like the Turing machine moment for data. What I mean by the Turing machine moment is we think we basically finally have an abstraction that's powerful enough such that it's not like a marginal improvement, it's like an order of magnitude improvements. The same way electrical circuits basically got turned into like extremely powerful beasts when we figured out how to program them and make them general. It was not like an improvement at the physics level, it was an improvement at the mental model level. So another way to say that is we think cryptography is a way to get more out of data. And most people will tell you that cryptography is a way to make data more private or whatever. I think that that's a great side effect, but deeper than that, cryptography is a way to get more out of data. Essentially make data more interoperable, be able to get data out of their silos, reap more economical benefits out of data. And it's pretty important because we live in a world where the value of data keeps increasing over time. One way we like to put it is we take data out of their data prison. Today, if you want your data to be safe and secure, it's useless. You have to like kind of like keep it for yourself. And it applies equally for like individuals who want to do self-custody, but also for companies. Like, why keep your data on your Linux server if you can put it in the one big database, you know? Because the one big database will like give you more value out of that. So there's kind of like this push and pull between people want to keep their data kind of like away in some sense in a secure environment, but that's equivalent to a prison. You know, you can't go screw with the inmates, but the inmates are not useful to society. And another way yet to say that is it enables more interoperability in usage of data. So our goal is to create more total value out of this, and at the same time enable a pragmatic route towards data ownership in a world where data keeps increasing in value. Because if data keeps increasing in value, the burden of proof for going through that route keeps increasing. Okay, so this is kind of like the TLDR on the data stack we have so far. We have pods, which are essentially specially issued packets of cryptographic data, almost like a record in a database. We have these cryptographic machines called GPCs that ingest pods and make claims about them using zero-knowledge proof. And the really interesting thing with this system is it's performant enough to run on mobile browsers while being flexible, and it's close to being production ready. And all of you guys are using it. Zupass, where your tickets are and your frogs is running on pods and GPCs. So as an example, a Devcon ticket is a pod, a frog is a pod. I used GPC to log in into the Telegram group where you had to prove you had a ticket. When you enter the frog zone downstairs, you also make a GPC. So this stuff just works, and there's a huge, like, not huge, but there's definitely a list of like, on top of that, like third-party application that is built on top of this system, mostly from the Zuzalu ecosystem. So here's the TLDR. The way it works is some authority attests to some data and signs it via an EDDSA signature on the job curve. This gives you a pod. You take a bunch of pods, you put them into a GPC, and you make a claim that is verifiable, and then you can hand that over to a verifier. That's essentially how it works. We'll go into the details. So the issuer basically calls this like pod.sign method on a bunch of key value data. You get out of it this thing with a signature that is on the content ID. We'll focus on the date of birth here for the sake of the example. Then you configure a GPC config, which makes a claim about the date of birth for this example. Here, it's not revealed, and we prove that it's between a minimum and a maximum. And then finally, a verifier receives the artifact from the proof and can verify that claim. And a really cool thing is you don't need any new zero-knowledge circuits. It's pretty flexible and also extremely performant, right? So we have this system. We've been working on it for a year. And you can go check it out tomorrow at Classroom B at 2:30 p.m. But last summer, we wanted more out of our system. Like, this is pretty sweet, but we think this is far from being the best we can do. So if we look back at this paradigm I just showed you, there's a bunch of limitations. The first one is we need specially issued data. What this means is we need to convince data attesters to like change the way they issue data, which is not very pragmatic. It's limited to one round of computation. You can take pods, put a GPC on top, but what you get out of it is not another pod. It's like this thing that you can't keep computing over. And finally, it's very much limited to single-player use cases. What I mean is when you create this GPC proof, you actually need to know all the input pods, which means that if you try to do it together with multiple people, one person will know all the inputs. So this is not compatible with the world we're in today, if we're pragmatic about deploying this beyond, you know, things like Zuzalu, Devcon, etc. First, there's a lot of cryptographic data, yet it's very heterogeneous. Stuff that comes out of trusted execution environment, blockchains, email, transport layer security, national ID systems, etc. All of this is cryptographic, but it follows different schemas, different signature schemes, etc. Basic use cases often require more than 2 rounds of transformation, like you want to transform your data multiple times across multiple people. And we think that there's a whole world that might open up if it's actually possible to go more than 2 rounds. If you think about the internet today, we never have like platforms that go more than 2 levels deep. You know, it's like we're building on top of mud huts and we dream of skyscrapers. We don't really know what's going to happen if we can go deeper than that. There is a lot of work on domain-specific system from the cryptography perspective, but yet there's absolutely no interoperability. Over the last 18 months, none of the ZK ID systems actually work with each other, you know? So it's pretty interesting, like why? And from the programmable cryptography perspective, the unlock of zero-knowledge proof is trustless refactoring and import, right? That's the right way to think about it, not as like a way to hide data, in my opinion. And you can use it to now create a universal system for making claim about the world's data. And the unlock of fully homomorphic encryption or co-snarker MPCs, now you can combine that data confidentially. So we want to put together a system that makes use of these primitives and is like situated in a world like this without being wishful thinking about like, oh no, the whole world is gonna like issue pods with EDDSA job signature, whatever, like that's not gonna happen. So what we want is we want verifiable and interoperable computational graph. So we want to import data. I think it's about emails, API calls. This is like a mobile driver license from the state of California. We want to turn that into pods. We want to compute at arbitrary depth with an arbitrary number of participants on this data. And finally, we want to export a view of this data to a verifier that can check the integrity of all the computational graph and the integrity of all the imports via like a single succinct proof, right? That's where we want to get to. And so that's putting it together. Again, the goal for a second version of the stack is we want to be able to introduce anything trustlessly. And the reason trustless is important, it's not because we think that, oh, like, you're going to be censored when you like import your like RuneScape character or something like that. It's more like if it's trustless, it's scalable because any computer can do it, as opposed to having like some bottleneck in the system somewhere. We want deep computational graphs because actually today we've never really seen what would happen if many parties were to be able to operate on a piece of data and kind of like pass it along, right? Most of the time you have data that gets ingested by one big group of people and then it gets consumed and that's it. And we also want to do it between multiple people while maintaining confidentiality because we think this is how you can tap into much bigger economic output. Okay, so the first challenge we had when we faced this, which I think not many people have thought about, this is probably the most interesting challenge, is program composability. So imagine you have a list of friends. It's probably like a list of pods that you've received, like each of your friends signed something saying they're your friends. You can put it in a program, here it's some Rust, but anyone can read this, which counts the amount of best friend you have. Best friend is just like a property of friend, and you get out 13. Now you take this and you put into another function that says, hey, do you have a great friend groups, which counts how many best friend you have. Here it just counts, hey, is it bigger or equal than 3? And you get a Boolean out, true or false. Okay, seems simple enough. Here's how it looks like more abstractly. You have some pods that go into program A, gets a pod out, go into program B, get a pod out. Okay, so assuming we can do this cryptographically, what problem remains? Well, the main issue is if you have a program that operates over the output of a different program, you need program B to understand program A, right? Either via static analysis, either via formal proofs, but program B needs to know what program A does. So unless you write program B after having written program A and kind of like hard code the link between them, it's really hard for a program to make sense of the output of another program. If I tell you 42, and I don't tell you how it was computed, it's really hard for you to know even what the significance of that output is. And we don't really think like that most of the time. Like when people say, oh, we'll have ZK VMs and then we can solve everything, the main issue is that, yeah, good luck now doing static analysis and kind of like trying to make sense of other programs. And at the end of the day, it reduces to the halting problem. So what we did is we threw away the CPU model and we went to logic. And we threw away the opcodes and we moved to logical operation. So instead of a virtual machine built on RISC-V or something like that, we built a logic virtual machine. We replaced memory slots with logical statements. So statements like A is greater than B, or there exists C such that C is part of D. We replaced opcode with logical operation. So as an example, A smaller than B implies A is not equal B. Or if you have A defined as 10 and B defined as 10, you can derive A equals B. All of these are like basic logical operations. Data becomes theorems. Programs become proofs, not the kind of proofs that you know about if you're a cryptographer, a different kind of proofs. Now we're going to mix all the words together. And it's like a pretty interesting way to look at the system. Essentially, what we have is data that gets imported are axioms. They're combined into a logic, like through a logic proof, they get combined into a theorem, and then more theorems can build theorems, right? So the interesting thing with that is all of mathematics is already built on that principle, which is every time we prove something, we can prove more out of it. And we don't need to understand what has been done so far. Like mathematics is truly interoperable in a way that programs are not. So if we get back to this example, you know, after we've counted how many best friends you have and want to know whether you have a great friend group, what this turns into is you have a theorem, and through another logic proof, you get yet another theorem. In plain English, you would have theorem blue, I have 12 best friends, implies theorem green, I have more than 3 best friends. Makes sense, right? So now we have 2 kinds of proof in the system. We have a formal proof and we have a zero knowledge proof. The ZK proof is used to show that the formal proof was computed correctly and hide some inputs about it, right? You want to be able to say, I have more than 3 friends without showing who your friends are, right? So, and you can kind of like go arbitrarily deep here. You have theorems, you make proofs. Out of that, you get a new theorem. You combine that with a previous theorem, maybe for someone else to make more theorem, and so forth. Here's how it looks like in a very early version of our system. So these are statements. These are the actual things that are inside a pod. So the most basic statement is the value of statement, which is that the value of an entry is this. Like the value of is best friend is true in the specific pod. This is how most people think of cryptographic data. They just have the value of statement. They don't have anything else. But then we added a bunch of other stuff, like the equal statement, which is this entry is equal to that entry. Or the sum of statement, which is that the sum of the two the entry number 2 and 3 in the tuple equals entry number 1. And this is like a very early version that we had, but you can imagine extending this to something that is powerful enough to essentially prove anything in first or second order logic. And these are our opcodes. As an example, we have the equality from entries opcode, which says, hey, if you have entry 1 and entry 2, you can apply the equality from entries opcode only if entry 1 equals entry 2 to get a statement that says entry 1 equals entry 2. What we had to do from a cryptography perspective is essentially build a circuit that, instead of proving the state transition of a CPR architecture, proves the logical operations on statement is done correctly, right? It's a cryptographically verified theorem prover, if you want. Okay, so the second challenge we had is we want to be able to import data from the real world, because we don't expect people changing the way they issue data. It was already sufficiently hard to get them to export cryptographic data in the first place. Good luck coming back to them and telling them they did it the wrong way. So what this turns into is you want to be able to turn any verifiable piece of data into a set of value of statement with special metadata. As an example, who signed it, what was the URL if it comes from like a web proof, when was it signed, etc. Right? And then you can further combine these into any other pod using the logic. So what if I want to compute with one of my frog, right? You guys have frogs. I hope you have frogs. If you don't have frogs, you're a loser. You need to go get frogs. Frogs are pod 1s. Pod 1s, as I was showing earlier, was the first version of our cryptographic data system. From the perspective of pod 2, they're foreign cryptographic objects. They're on different curves with different signing algorithms. They're merkleized in a different way. Yet they can be imported via what we call an introduction gadget. So you have this introduction gadget that is going to verify the EDD sig is correct. It's going to store the signer into a value of statement with key underscore signer. And it's going to copy each of the pod 1 entry into a value of statement. And then you get a pod. And the cool thing is now you can take 2 frogs, you can introduce them, and then you can make a proof about them. You can say Todd is more beautiful than the MA mustache toad. That's something you can prove with the system after you've introduced the data. And the first thing we want to do is be able to import emails. We want to be able to import like regular API calls and probably deal with one of the government-issued ID system. But then over time, you can imagine importing things from Ethereum, importing things from virtual worlds, importing bank accounts, receipts, or even like actual mathematical proofs, and keeping generating statement about these. Okay, the third challenge we had is making building easy. This is what it looks like to put together a sequence of logical opcodes, and it's extremely gnarly. Don't ask us why we have strings. It should be pointers. It's a whole story. And making sense of pods or crafting them becomes very tedious and easy to get wrong, right? The users of the system need to craft a sequence of logical opcode to make a new pods. But on top of that, they need to make sure that the statements they get out when they receive a pod actually match what they're asking to be proven. If you get this, you know, all of these logical statements, like it's hard to know whether this actually proves that the person matches the claim you're trying to like verify. So what we did is we put together a little Lisp. It's a logic programming language to create pods and verify them. It's a Lisp because it's really easy to write a Lisp versus other kinds of programming languages. And it has an interactive development loop. Here's what it looks like. So here I'm just making a pod. Technically, this is an introduction gadget because I'm making data out of nowhere. So I say, hey, key age is 26, zip code is such, ID is such, and what I get is a bunch of value of statements, including a magic one, you know, the underscore signer one, which points to who created it. And then I can make more pods out of it. So let's go through an example. Here, I'm going to make a pod that says, I have both an ID card and a pay stub, where the user ID is the same on both, and my age is over 18, and I think that's about it. And I reveal my salary, right? So first what I'll do is I'll query for a pod using the pod question mark statement, saying I want a pod that has an age value, a zip code value, and an ID value. And I don't care about anything else. And I bind them to these variables. Then I do the same thing for another pod that has a salary, a timestamp issue, and an ID. And I'm going to reveal zip code, salary, timestamp issued with the same key name. And I'm going to make some assertions that age is over 18. And then I do a join. I say ID card ID and pay stub ID are the same. The cool thing is I'm going to be able to prove that ID card ID and pay stub ID are the same without revealing the ID. That's the thing that's very powerful about it. What I get out is a bunch of statements. And you kind of have to trust me on this because it's small enough, but the ID is not revealed in the pod itself. The fourth challenge we had is multi-party pod creation. So today, if you're on the right side, like the little smiley guy there, the red pods are private, right? You only see what's in the yellow pod. But if you're the person on the left and you're putting the proof together, you actually get leaked the input pods. So what we want to be able to do is essentially put a box around proof calculation. I'm talking about the formal proof, not the ZK proof, such that the input pods are not leaked across the party, right? And we were hoping to get a demo of this by Devcon, but of course, it did not happen. The rest happened, but not that. So the way you solve this is you execute logical operation into either a multi-party FHE or something like verifiable garbled circuit or co-snark. In order to do this, you also need to crack verifiable fully homomorphic encryption without multiplicative overhead, which is tricky. I won't talk too much about this, but if you're interested, come to the programmable cryptography CLS on Friday. So that's pod 2. It's a system that can import data that is cryptographic regardless of where it comes from, enables deep computational graphs, and then you can export whatever view you want on the data with a succinct proof to a verifier. It's logic-based, both for its claim and its operation, and has a bunch of cool features. It's in active development right now. We hope we'll have a production-ready version by end of 25, and we'll probably go through a bunch of pilots throughout the year. If you're interested to learn more about it, so first, if you're interested in pod 1, which you can use right now to build stuff, it's tomorrow at Classroom B at 2:30 p.m. And if you're interested in pod 2 and PEX, we're running a pretty long and interesting workshop on Friday at 12:30 p.m. at the Programmable Cryptography CLS. So I'll keep the QR codes up for a little bit, and then I'll be done. So thanks, guys.
Thank you so much, Justin. And we have a ton of questions. So look into the questions and start answering them. We have 3 minutes.
Oh, so you're not going to read the question, I have to do the work? Okay, cool. All right, you mentioned first order logic, also second order. Those are not computable logics, they're just computable and enumerable. What am I missing then? Because you're computing for sure. This is true. So our logic so far is a bastard logic. It's a logic that is not actually the kind of logic that logicians use. So an active area of research is figuring out how do we essentially like have a logical system that is also computable in a way that is like as sound and complete as possible. And if you have asked that question, please come talk to me because we're very interested in that. So great question. Running this in the browser means you need to trust the server to serve a non-compromised version of the software. How will this work in practice? Are we going to have an open standard for pod processing? Okay, so if we go down to the level of like, well, you have to trust the software you use, I have a bad news for you, which is it's a problem for all of the industry so far. So the way you'll solve this is the way you'll solve everything else. So I don't think I want to answer this question. What's next? Can you scroll or something?
No, they will scroll it from there.
I got there late. What is this for? It's for making data useful beyond this stuff that we have right now where we just store them in databases and we sell them to OpenAI. Okay, I think that's it. Thank you.
All right, thank you so much, Justin, for this session.